So question number 1, who can help me? New domain and range. Abir, could you help me? Huh? And we'll keep the ends as they were. So again, because we have this x plus 2, that means it's moving to the left by 2. So if we were thinking of mapping, and I think we looked at this question yesterday and we talked about describing it in words and also mapping. This would get mapped to x minus 2, so it moves to the left by 2. Good. And the range, somebody? Yes, Nazifa. So 13, 18, keep the endpoints as they were, because both decreased by 1. That would be the mapping notation. So mapping notation can be really handy as a way of kind of looking at the question, doing a quick summary kind of what's happening, and then just using that idea to change the domain and change the range. And even when we're graphing, we could use it to adjust points that way as well. Questions with 1? 1 is good. On to number 2. Cushman, could you help me with the domain for this one? Okay, so it'll want to switch the order, so we have the smaller one on the left, -5 and 1. And what brackets do each of them get? Square bracket here, rounded there. Yes? Agree? I'm seeing some uncertain responses. Anybody want to disagree? Yeah, Cam? Include the 1 but not the -5. So if we thought of the original and we just kind of imagined a number line, this was at -1 and that's at 5 like that. The negative sign in here changes the signs on the x's. So again, if we were going to write the mapping, xy gets mapped to -x, comma, y, so the y won't change. So if we're changing the sign on the x's, then this will become a positive, this will become a negative, but does anything happen to the dots at the endpoint? Do they change? No, they're going to stay as they were. So the bracket kind of travels with the endpoint. We could think of it that way. So that this 5 was not included, so the -5 also not included. The 1 was included. Whoa. So now the positive 1 will be included. So if you just imagine that the endpoint or the bracket that's beside the endpoint travels with it, that can help. Cushman, is that good? Okay, thank you. And as I mentioned, there's no change in the y value, so the range will be the same as it was before, 14, 19, not including 14, but including 19. Okay. Number 3. Let's start with the mapping. Who could tell me what the mapping would look like for number 3? Probleen. Like that? Yes? Agree, disagree? All those in favor, give me a thumbs up. All those not in favor, uh, thumbs down just seems so harsh. But let's just get the information. Thumbs down if you disagree. Oh, quite a few people disagree. Probably. Why do you think that is? Meant -4. Is it getting better? I'm seeing some nods and some head shakes. So if we change that to -4, who thinks that's better? Who thinks that's not better? Oh no, Pravleen. Oh no. Is it? Huh. Well, let's do it correctly today. I don't remember what I did yesterday. Anybody else know what I did yesterday? We need more witnesses. Well, we'll see. So this should still be a plus. So again, because this 4 is not grouped with a y, it does exactly what it's looking like. So it's affecting y values, but it's not on the same side as the y in the equation. So the +4 does mean it's going up 4. But what's the thing that we should change? Peter. So instead of the negative here, we need to have a negative with a y. So that's kind of small for people who are far away. So now we have x plus 3 comma negative y plus 4. If you agree, give me a thumbs up. Now I'm seeing lots of thumbs up. Yeah, so when we have the negative sign out in front of the function, remember function values are y values. So this is changing the y values. So it is a reflection in the x-axis, but the y's are changing signs, so we need the negative sign there. I just didn't leave enough space. So, domain and range. Tuba, could you give me one of the two, domain or range? And the brackets will be like this. And somebody give me the range. Artie. -15, -10, and what brackets should they have? Like this. Okay. Quick 20-second chat with your neighbor. Do you agree with these two? Yes or no? Okay. That was more than 20 seconds. But how many people are 100% confident that this is correct? Okay. Anybody? 80%, I think it's right, but not 100%. Anybody for that category? Ooh, anybody say 100% is wrong? Okay. What about 80% it's wrong? How about, I kind of don't want to commit to anything today? Oh, some of you are committing to not committing. I appreciate that much, at least. And many of you are not committing to not committing, which is fairly consistent. So I can also appreciate that. Okay, so somebody needs to present a case here. Either a case that these are correct or a case that it's not. Let's start with domain. Anybody like to present a case? I believe the domain is correct or incorrect, and here's why. Yes. Sorry, can you say it again a little louder? one up here plus 3 would give us this 2. And then the 5 plus 3 would give us the 8. So you're saying it is correct? Pardon me? Two and 8. So how many of you now are convinced the domain is correct? Who is convinced the domain is incorrect? Who is still not committing to anything? Lots of non-committal people. I believe it is correct, yes. Because again, yep, just as it was described by Armahan there, if we start with those 2 x-coordinates and we add 3 to both, which is what we have from our mapping here, we get the 2 and the 8, the brackets stay where they were. So it's kind of like, again, if we look at this number line that I drew here, what we've done is we've taken this whole thing and we've just shifted it to the right by 3 units. So the endpoints, don't do that. The endpoints stay as they were, as in closed at the left and open at the right. Just that whole domain has shifted, and so my left end becomes a 2, my right end of that interval becomes the 8. So yes, domain is correct. Big check mark. Now the range. So I think I want to give you another minute to talk to your neighbor and see if you can come to an agreement on if this is right or not right and why. Okay, so take a minute, talk to your neighbor again. Okay, let's go over the range. So hopefully you're convinced, but let me just talk it through here. So here's the original range we had, open interval at 14, closed interval into the interval at 19. So there's the original. And then we said we had this mapping. So I got the mapping from here, negative y plus 4. So I've just rewritten it here, negative whatever the y value is. So I just put brackets instead of y plus the 4. And I did that for both values. So again, open interval on the left, closed interval on the right. And I'll just plug in the numbers. So I plug in the 14 here and the 19 there. So negative 14 plus 4, negative 10. Negative 19 plus 4, negative 15. And the endpoints stay with them. So this is still rounded, that's still square. But then we look at this and we say, is this in the correct order? Is the left the smallest and the right the largest? It's not, so we do need to flip this thing around so it's in the right order. When we flip it around, we do get the range that we'd written up there from negative 15, including that, up to negative 10, not including the negative 10. So that was correct. Excellent. Questions? No questions? Okay, so with the conversations I heard, there's a bit of discussion as in which do we do first? And that we're going to talk about more once we combine more transformations together. So we're kind of looking ahead as we combined reflecting and translating. And kind of the general rule is we work from left to right, the same as when we're reading, but there's some variation that we could have. Kind of like with multiplying and dividing, we work from left to right, but multiplying and dividing, because they're very similar operations, dividing is the same as multiplying the reciprocal, we can actually do them at the same time unless we have addition subtraction in there. So similar kind of thing here. But we'll get to that more in a future lesson. So in your notes, we're going to look at 3.3, stretches of functions. And a quick comment here that your workbook will use the terms, what will it use? Expand and compress. Alberta Ed will not use those terms. Alberta Ed will only use the term stretch. So I will only use the term stretch. So when something gets bigger and as it's stretched out, we call it a stretch. If something gets smaller as it's squished in, we call it a stretch as well. Okay. The reason for that is because there can be some confusion. If you say there's the stretch by a factor of 2, it's fairly clear. An expansion by a factor of 2, the expansion says it's getting bigger. The 2 says you're doubling everything. If you have a compression by a factor of a half, that's where it gets confusing sometimes, because the compression means it's getting smaller. The factor of half also means it's getting smaller. Is that like a double negative that actually means it's getting bigger? So because it's caused some confusion in the past, Alberta Ed decided we're just going to call it stretching and make it all simple. Okay, so we use the term stretch only. Here we have again, review question. So we have a function that we're given as a graph. Then we're going to do a translation on it in the second grid. Then we're going to do 2 reflections in the third grid. And then the last one, we're going to have a combination of translating and reflecting. The last one's going to be a little bit tricky. So make sure you're using pencil. In case you need to make corrections, I'll give you a few minutes to try these. I'm going to interrupt you at this point. I'll go over the first 2 and then talk about the third one and then give you another minute or 2 with the third one. So, as we look at the second equation where we have the f of x plus 2 in brackets then all plus 3, the x plus 2 grouped together, it's affecting x's, so it does the opposite of what it looks like. So instead of to the right by 2, it's to the left by 2. So every point is going to move left 2 units. Then we have the plus 3 outside the function, which means it's going to affect y's. It's not on the side where the y variable is, so it does exactly what it looks like, which is that it's going to move up 3 units. So every point moves left 2 and up 3. And so then you can just kind of count it out to see where it's going to be. Now, what some people like to do is they like to use the mapping and basically write down the mapping kind of as an algorithm. Anybody know what an algorithm is? An algorithm is a set of rules, basically. So the nice thing about an algorithm is that you have to do some thinking to create the algorithm, but once you have the algorithm made, there's very little thinking involved. It's very mechanical. So computers love algorithms. A programmer needs to think through how is this going to work, what is the process we have to go through. So the programmer creates the algorithm. Once they stick it in the computer, that's what the computer likes, and then it just does the process. Computers aren't good at thinking. They're good at doing simple tasks really fast. So what we could do for this question would be to say, well, my mapping here is that xy is mapped to x minus 2, y plus 3. And then we could set up a little table with all the points. Let me just give a disclaimer here. This is not my preferred way of doing things, but some people really like it. So I'm going to show you. So I could pick kind of each of these significant ordered pairs, and I'll just pick a couple of them. So we have -4, 4. And then the next one, -2, -2. Then we could list it out for kind of all the key points. And once I have my algorithm, which is this mapping, then I can just apply it to each point. So x is decreased by 2, so -6 and -4. Y is increased by 3, so 7, 1. And I don't really have to think, I'm just number crunching, right? So I get the number crunching, I come up with this ordered pair, and then I can plug them in here, and I can see, oh, this is -6, 7 was that point up there, and -4, 1 was this point here. Advantage to this is you do the serious thinking up front, and then you just do number crunching, which is really low-level thinking, and then you just plot those points. The disadvantage is, if you make a mistake, which I've seen students do, they'll plot a point and then they don't stop and look at it to say this shape isn't right. So you always want to look and say, is this the right shape? Whenever we do a translation, the shape doesn't change. So we'd say, in this second graph that we drew, the shape that we have is congruent, same size and shape as the original. Translations don't change that. Reflections will change the orientation but won't change the shape. Once we start stretching, then the shape gets changed. So if you like the algorithm way, you're welcome to do it. But a word of warning is that once we get into trigonometry and we're doing transformations like this, it's faster to do it without thinking through algorithms, without mapping every single point or all the key points. So if you're ever confused, this is a good way to do it, because the mapping you can think through. We've practiced mapping a little bit, and then it's fairly basic thinking after that. But I would encourage you to think about what's happening to the graph and think it through in a more visual way. So I'd encourage you to push yourself that way. Okay. So sometimes what that means is it's useful to sketch intermediate or in-between graphs. So for this third one, let me try. If I was to graph y equals negative f of x. So I'll say I'll just do one of the reflections first. So the negative sign is in front of the f of x, which means y values are changing. So this first y value here that was at a positive 4 reflects down and it's going to go to negative 4. So I'm going to have a point, negative 4, negative 4, 4. That's where this first point would be mapped to. The next point, negative 2, negative 2. Again, the y values change, so negative 2, positive 2, it's going to end up there. Next point, 0, 2, change the y values, 0, negative 2. Next point, 2, negative 4, change the y to positive 4. And then the last point, which is 4, 0, will still be at 4, 0, because the negative of 0 is still 0. Pravleen. Yes, but as I said, first I'm going to demonstrate what if we just do one reflection at a time. So that's what I'm doing so far. Okay? So we could do both at the same time, and some of our brains are going to be able to do that relatively easily. But for some of us, it's useful to put in a transition. So this would be the transition where I've only changed the y values. So when I come to drawing my graph, I would connect these points. And again, this isn't the final graph I'm looking for. This is just y equals negative f of x. So once we've done this one, then we can go and we can do the other part, which would be to say, well, let's reflect all the x's. So now, this point is going to be reflected there. This point, this black one will be to there. Maybe I should do colors, but I won't. This point is invariant. It'll stay there. This point moves there, and then we get a point here. So my final graph should look like the red one. So as you can see, there's a disadvantage to using this method as well, because I have multiple graphs showing up, which is the correct answer. So if you choose to do this, you just need to make sure that you clearly identify that this red one, well, let me do this, is actually the graph that I'm aiming for. And so you may even want to draw the earlier ones with dotted lines. just to indicate that it's more of a guide rather than your final answer. Or you may just want to plot the points and then kind of do the second reflection on the points and then just draw it in. So another way we could do it, again, we could have done this with mapping. Mapping would have been fairly easy to do. We write the mapping out, and then we apply it to each of the key points and then plot the new points. But then again, make sure you stop and look at the graph. Is this the shape it should have, or does something look off? Questions with that one? Nope. Okay, the last one. Oh, yes. Domain and range. Yes. State, domain, and range. Thank you for reminding me to do that. Let me just erase this so I can use the space underneath. For the original, my domain was from -4 to +4, including those endpoints. And the range also -4 to +4. Then for the first graph, all the x's decreased by 2. So that's going to be -6 to 2. All the y's increased by 3. So that'll be -1 to 7 for my range. For the next one, I switch the signs for both. So my -4 for my domain becomes a +4. +4 becomes a -4, so my domain is actually going to look the same as the original. And the same thing for the range because of that symmetry we initially had, same distance to the left and the right of the x-axis, or above and below the x-axis. Questions with that? Nope, we're good. Okay, last one. We need to do some manipulating here before we actually get going. And so what I'm going to do is I'm going to take this 3 and I'm going to add it at the end. So I'll have y equals negative my function, and then the +3 at the end, just because that's more typical for how we write things. So that indicates to me that because it was a +3, it's still a +3 at the end, which means the whole thing's going to be moving up. The next thing I have to do is, inside here, I need to factor out the -1 from those terms, so that I'll have a negative times x minus 2. So we haven't looked at this yet, but in order to recognize all of the transformations that are happening, in this case reflections and translations, we need to have an x with a coefficient of +1. So we get that putting in the brackets, we factor out the negative. This negative that's out in front here, trying to make this clear for people who may watch the video. So the negative out there tells me it's going to be reflected in the y-axis. X's are changing. But because I factored that out, now this sign has changed, and I know that it's going to actually translate to the right by 2 units, which it didn't initially look like. That's why it was critical that I factor that out. So it's going to be a reflection in the x-axis and in the y-axis, translated 2 units to the right and 3 units up. Saw it. Because I don't know what that function is. So Saad's question is, why can't I just take out the negative? So maybe I'll just do a new page here for a second. Suppose I had f of x is equal to x minus 3. Suppose that was it. And then I change this to, let's say, the negative. Well, that's not a good color. Let's go of f of negative x. So suppose I was going to look at that. What happens to my equation? Well, this part tells me my x is replaced with a negative x. So I'll have a negative x, and I still have the minus 3, but then this negative that's in front applies to everything. So what I end up with is a positive x plus 3. So it's changing things in a variety of ways. So I couldn't just take out this negative and say, oh, the two negatives will make it positive, because the result isn't identical to my original function. Or, suppose we had something a little bit different. What if I had f of x equals the square root of negative x? First of all, does this exist? If x is negative 9, can I square root the negative of negative 9? I can. So this is a function that exists. There's a restriction on the domain. But if I put a negative sign inside with the x, that's going to change this sign here, which again is going to be a reflection. So the original function would have looked kind of like that. But with the negative in here, it's going to reflect it, and it's going to open up in this direction. So the functions look different. And so here I looked in terms of the equation, but if we even just think about what's happening, if I do a reflection in the x-axis and a y-axis, that doesn't return the function to its original location. So we can't combine those together. Is there another question? Yes. Why do you have to factor out the negative? Because otherwise I can't see what the correct translation is what it comes down to. So we're going to get there eventually, where we're going to say our standard form, we're going to have the x isolated in here, we'll have a 1x plus or minus something. That has to be the case in order for us to see what the translation is. So what we're doing is we're just saying that's just how it works. We're observing and we're learning from it. Okay? So, now that we know that this is the equation that we need to graph, based on that equation, can you have a look at that third graph and make some guesses about what it should look like? I'm not going to give you much time. So then as we look at the second table, now we have this 4 out in front of the function. And so compared to my original, it's just going to take all the y values and multiply them by 4. Because the y values were all the square root of x, and then it's times 4 in front. So all the y values get 4 times as big. So I'll have 0, 4, 8, 12, and 16. And then I'll plot those points. So you don't need to draw those green lines in, but I'm just going to use them as a reference. So if I look at the length of those green lines, and then I look at the length of this yellow line compared to it, oh, that's how fat I wanted the green line. Okay, I'll redo the green line so they're this as well. Oh, green. Oh, there's my green. If I compare the green and the yellow, I don't want to think how much longer is the yellow. I want to think how many times as long is the yellow, because that's what a stretch is doing. Because if I think how much longer, then this first one, so this first one here I'd say is 3 more. This one here is 2, 4, 6 more. That one there is 2, 4, 6, 8, 9. Wait, 1, 2, 3, 4, 5, 6, 7, 8. It's 9 more. So yeah, there's a pattern, but it's not the best pattern. So if I go back and I think about how many times as long is it, well, here my original green line is 1, and then the yellow line is 4. So it's 4 times as long. Here my green line is 2, my yellow line is 8. Oh, 4 times as long. 3, 12, 4 times as long. So that's what's happening. Every y value is getting 4 times as big. So we'd say it's being stretched vertically. And to be more precise, we'd say it's being stretched vertically about the x-axis. So any point that was on the x-axis is still on the x-axis. So that would be an invariant point there. Okay, so there we have the vertical stretch. Good with that? Yes. Exactly, yeah. So what the A value did last year, thank you for bringing that up. The A value was a vertical stretch factor. Now, if the A was negative, then it opened down. This year, we're thinking of it, well, don't just think it opens down, but think, oh, it's reflected in the x-axis. So just like last year, if you had y equals x squared, you'd have parabola like this. If you had y equals negative x squared, you'd think, oh, it opens down. But don't think that this year. Think reflection in the x-axis, which results in it opening down, but not every function is going to be opening up or down to begin with. So it's best to think how is it reflected rather than what the direction of opening is. So then we come to the next table. And I'm just going to remove, oh, excellent, a bunch of things out of the way, sort of. Okay, down. Okay, there we go. Now we have a little bit of space to work here. So horizontal stretches are a little bit tricky. So let's just pick some x values and figure out some y values. So that's not how I did the table here, but suppose I did. So if I have y equals the square root of 4x, if my x value was 1, what would my y value be? It would be square root of 4, which is 2. Okay, so suppose my x value was 4. What would my y value be? Pardon me? 4. 4 times 4 is 16. Square root is 4. Okay, so initially I had 1s and 4s in my table, and as I look at this, I can see, well, I found 2 of the points where my y value is 4, my x value was 4, where my y value is 2, my x value was 1. So I figured out those points looking at the table in blue below. If I make a comparison over to here, how does this x value compare to that corresponding x value? So notice for both of those, I have the y value of 2. So I'm looking at what's the relationship between those two. that's the same as the relationship between those two. What's happened to the y values? Back. It becomes a fourth. Yeah. So, remember back here, if I had f of x plus 2, it looks like 2 is being added to x. But we've learned, grouped with a variable, it does the opposite. So it actually was to the left by 2, or the x values decreased by 2. Same thing happens here. If my stretch factor is grouped with a variable, it does the opposite of what it looks like. It's not multiplying x values by 4. It's making all the x values 1/4 as big. The 4 becomes a 1. The 16 becomes a 4. So, just like with the translation, grouped with a variable does the opposite of what we think. So, as I look at my values here, 1/4 of 0 is still 0. 1/4 of 1 is 1/4. I'll just put it as a decimal. 1/4 of 9, 9/4. So those aren't going to be very nice points to plot. We have a couple, 3 nice points that we can plot. At 0, 0. And then 1, 2. And then 4, 4. So here's what happened. This x-coordinate that was a 16 got multiplied by 1/4 and is now 1/4 as big. So that arrow isn't a translation. That arrow is just showing me how it shrunk down. So my graph squished horizontally. So we'd say it's stretched horizontally by a factor of 1/4. This point here is now 1/4 as big, and it's at 2 1/4 there-ish. This point here is now 1/4 big, and so it's way in there somewhere. And so I only have a little piece of my graph, but we'll just say that's enough to do a sketch. And the graph will kind of go like this. Not super precise. Okay. Now, depending on the function, sometimes a horizontal stretch and a vertical stretch can have the same result or can look the same. If we come back and we think about this equation that we had here, y equals the square root of 4x. Could I simplify that? If we were thinking grade 11? Yeah, what would we do? Y equals 2 times the root of x. So, this is telling me that a horizontal stretch by a factor of 1/4 looks exactly the same as a vertical stretch by a factor of 2. So I come back here and I look at this and I say, oh yeah, this is twice as much vertically. This is twice as much vertically. It should be that this is twice as much vertically. My graph is not too bad. So, if you were given the graph and you're asked, well, what's the stretch? You would have some options in this case. But if you're given this equation as it is, we want you to explain based on the given equation, not a manipulation of the equation. So if this is what we were given where the arrow is pointing, we'd say it's stretched horizontally by a factor of 1/4. Questions? No questions? Let's look at the next page. So here for number 3, we're going to do some practice. All 3 of these are vertical stretches. So you're given the original graph. You just want to sketch what does it look like when you stretch it vertically by these values. Those 3 should be not too bad. The next ones are horizontal stretches. Be careful with those. Notice the last one in each of them includes a negative sign. So there's a reflection and a stretch. Here as well, there's a reflection and a stretch. So just be careful when you get to those. And I'll give you some time to work. Can I have your attention for a minute? I'm just going to go over the third graph for the vertical stretch, and then I'll give you some more time to work on the horizontal. First two graphs that I've done, maybe I'll just do a quick comment related to those. So notice here my y value is 4 for that point. Doubling it gives me 8. So I can just think about the y coordinate, and this 2 says I'm doubling all the y coordinates. Okay? Or I could say the distance from the x-axis is being doubled. That's another way to think of it. Because we will only do stretches about the x and y axis, it's easy just to think, oh, I'm just doubling the y values. In the future in math that you do, you may be stretching about different lines. And in that case, it's easier to think about doubling the distance from wherever the reflection line is. And actually, when we get into trig, we're going to think of it that way. For now, we won't. We'll just think of doubling all the y values. Here, all the y values times a half. So I could do something similar here. Here, I could just take all the y values times -3/2. And in that case, I can move all the points at once. Or I can do it in small steps. What would you like me to demonstrate? Who would like, so the options will be, just multiply all the y values by -3/2, option 1. Or option 2, do the reflection first and then do the stretch. Who wants option 1? Who wants option 2? More people, so I'll do option 2. So I'm going to break it down into stages. The negative sign reflects all the y's. So here the y value of 4 will become a -4. X stays the same. My next -2 will be a +2. Next, the +2 will become a -2. The -4 will become a +4. And then the 0 stays at 0. So those points are for y equals -f of x. Up to there, any questions? Okay, so now I'm not going to draw the lines connecting them. I'm just going to do the stretch based on those points so I don't get too many lines showing up here. So I'm going to switch, and now I'm going to multiply all the y values by 3/2. So here, my -4 times 3 is -12 divided by 2, -6. My next point, y was 2 times 3 is 6 divided by 2, 3. My next one was -2 times 3, -6 divided by 2, -3. And then the next one will be a 6, and the last one will be the 0. So then I'll draw the line connecting those. And then I'll look at that and I'll say, does that look pretty much like this original function that I had here, but just sort of stretched and flipped? Or does it look like it's a little skewed or a little distorted? Because as I looked around, there were a few people that came up with graphs that kind of looked right, but then there's a bit of distortion in there somewhere. The proportions seemed a little bit wrong. And as people paused and looked at it, they could see it. And if you see something like that, that's kind of a flag that, oh, maybe I made a mistake in one of the points. Might have been a couple points, but often it's just one point. And then you just want to double check. Saad. Yep, if you wanted to do it in just one step, multiply y values by -3/2. It's better not to think about wider and narrower when you're looking at vertical stretches. Now, last year when you worked with quadratics, you did. You said, oh, if I had an a value of 2, it looked narrower. Really, it was stretched out vertically, and that's what made it look skinnier. So it's better to think of the direction that the stretch is happening rather than think wider and narrower if it's a vertical stretch. Other questions? Nope. Okay. A few more minutes for number 4. Oh, it's almost the end of class. Not many more minutes for number 4. We'll go with that. So there are my graphs for the horizontal stretch. So for the first graph, because I have this 2 here, the x's are all multiplied by a half. So this distance that was 4 becomes 2. And same thing with all the other points. For the next one, because I have a half there, does the opposite of what it looks like. So all the x values are doubled. So again, where this used to be a 4, now the distance is an 8. So horizontally, all the points are twice as far from the y-axis. But we'll notice that any point that was on the y-axis stays on the y-axis. That's an invariant point. So just like reflections, we have invariant points when we do stretches, and the invariant points will lie on the axis that we're stretching around, as long as we're only stretching in one direction. And then for the last one, again, if I start with this, that was 4 in the negative direction. This negative flips it, so it goes in the positive direction. The reciprocal, so it's going to be 3/2 again. So now that distance is 6, or 3/2 what it originally was. Okay, I've seen the hands, but I'm going to ignore them. Sorry, we're almost out of time. So I want to make sure I get to the summary. So here we have the summary. If we have a function in this form, y equals a, f, and then brackets b times x, we have a vertical stretch about the x-axis by a factor of not just a, but we'd say the absolute value of a. The sign, we'd say, is a reflection. So it's only the size of the number that tells us the stretch factor. Horizontally, it's stretched by 1 over the absolute value of b. So again, it's the reciprocal of whatever that number is multiplied to the x's. And I think that's as far as we're going to get with the notes. We have 3 minutes left, so now I can take a few questions. Abir, you had a question. Yes. So it is wider than this original. So originally that was 4, now it's 8. Oh, this one here? Again, it does the opposite. So if I have a 2 times x, it's actually a horizontal stretch by a factor of 1/2. Always the opposite of what it looks like. Yes? That will take more time than I have to explain right now. Hey, that'll be it for today.